Long before anyone mapped an artery or named a valve, people noticed one reliable sign of life: the pulse. It rose with fear, steadied with rest, and vanished with death. That simple rhythm made the heart feel like more than flesh. It seemed like a judge inside the body, marking danger and relief in real time. When emotions hit, the chest answered first. The pulse became proof that feelings lived somewhere physical. From that observation, a powerful idea took hold. Courage meant a strong heart. Grief meant a heavy one. Love made it race. People used the heart as the language of character because it behaved like character. It reacted before words came out, and sometimes before choices were made. In battle, in childbirth, in sickness, the body's signals felt like guidance. The heart seemed to warn, push, or hold back, even when the mind hesitated. But there was no clear mechanism to point to. No one had seen inside a living chest and explained how a beat happened. So meaning filled the gap. Cultures treated the heart as the seat of will, memory, and inner knowing, not because they proved it, but because the body kept suggesting it. The pulse did not ask permission to change. It simply changed. And that made the heart look independent, like it carried its own kind of sense. During the Renaissance, curiosity turned into a method. Instead of guessing what the heart meant, anatomists opened the body and looked. That single step changed everything. Inside the chest, the heart no longer seemed like a mysterious flame of courage. It had walls, spaces, and a clear layout. The organ that once carried emotions in people's minds started to look like something built to do a job. Dissections revealed chambers, separate rooms that held blood, and they showed that the heart did not feel like one simple hollow sac. It worked in stages. Then came the valves. These thin flaps acted like one-way gates, allowing blood to move forward and blocking it from slipping back. The discovery forced a new kind of thinking. Flow had direction. The heart controlled that direction. As early modern anatomy advanced, the heart's structure kept pointing to the same conclusion. It functioned like a pump. Not a symbol, not a seat of instinct, but a piece of living machinery. Blood moved because pressure pushed it, and valves prevented the push from being wasted. Myth lost ground with every careful cut and every drawn diagram. The heart became less magical and far more explainable. In the 19th century, the heart stopped looking like a simple, silent pump. Scientists began to notice something else riding inside each beat, an electrical signal. With better instruments and careful experiments, they saw that heart muscle did not just squeeze on command. It fired. One wave of activity led to the next, spreading through the tissue in a repeatable pattern. The beat had a trigger, and that trigger looked electrical. Then came the result that changed the argument. When hearts were removed from the body and kept alive for a short time, they still contracted in rhythm. No brain, no spinal cord, still beating. This was automaticity, the ability to generate a basic rhythm from within the heart itself. Nerves could influence the heart, but they were no longer the obvious starting point. The heart carried its own starter motor. That forced a new way of thinking. If a heart could keep time on its own, then the brain could not be issuing every beat like a command. Something inside the organ had to produce regular impulses, and the muscle had to respond in an organized sequence. The heartbeat became a built-in cycle, not a remote-controlled one. From that point on, the big question shifted from who ordered the beat to how the heart created it. In the early 20th century, researchers finally drew a clearer map of the body's automatic wiring. They called it the autonomic nervous system, nerve pathways that ran from the brain and spinal cord into organs that worked in the background. The heart sat right in the middle of this new map, and the key question stayed sharp. If the heart already beat on its own, what exactly did these nerves do? Experiments with stimulation and nerve cutting gave a consistent answer. One set of nerves, later grouped as sympathetic, pushed the heart to beat faster and stronger. Another, carried mostly through the vagus nerve, slowed it down. Speed up, slow down. That part looked clear. But something else stood out every time. Even when these outside signals got blocked or removed, the heart still kept a basic beat. That result forced a new separation of roles. The brain's nerves acted like a control dial, not an on-off switch. They adjusted the rhythm to match stress, rest, effort, and recovery, but they did not create the underlying timing in the first place. The heart's own automatic rhythm stayed the foundation. The autonomic system simply shaped it moment by moment, like a regulator riding on top of an engine already running. By the mid-1900s, researchers stopped treating heart muscle as one uniform mass. They had found a built-in wiring system, specialized conduction tissue that carried electrical signals along set routes. The heartbeat no longer looked like a simple wave spreading at random. It looked organized. The signal started in a natural pacemaker, ran through relay points, and then triggered the chambers in sequence. Timing became a feature the heart produced from inside itself. That discovery changed the next question. If the heart had dedicated pathways, then it could also have built-in rules for how to react when conditions shifted. Physiologists tested this by changing pressure, stretch, and chemical balance inside the heart and watching what happened. They saw fast adjustments that occurred too quickly to depend on orders from the brain. Certain areas sensed local trouble and conduction patterns shifted. The heart did not just beat, it responded. Those rapid adjustments looked like reflexes, but they happened within the organ itself. Small loops of sensing and response altered rate, force, and timing from one beat to the next. When filling increased, contractions strengthened. When signaling routes were disturbed, rhythms broke or rerouted. The big implication landed quietly but clearly. The heart contained internal circuitry that processed information on site. It acted less like a passive pump and more like a system that managed its own traffic. By the late 20th century, heart research entered a new phase. Scientists no longer asked only how the heart followed orders from the brain. They asked what the heart controlled for itself. When they traced nerves inside the heart muscle, they found something unexpected. Dense clusters of nerve cells gathered in small hubs, linked by fibers like a local network. These were not passing wires. These were neurons that lived in the heart. This emerging field became known as neurocardiology, and it treated the heart as both muscle and nervous tissue. Researchers mapped these nerve clusters around key structures, especially near the atria and the roots of the great vessels. The placement mattered. From there, the neurons could monitor incoming signals and send quick instructions back into the heart. The heart still listened to the brain, but it also listened to itself. As the maps filled in, the implications sharpened. These internal neurons sensed changes in pressure, stretch, and the chemical mix of blood, then coordinated responses through local circuits. They helped organize timing, adjust strength, and manage rhythm under shifting conditions. It looked less like a simple pump with a remote control. It looked like an organ with its own built-in command layer. That nickname followed naturally. The heart brain. The next step sounded simple. If the heart really held its own neural network, it had to do more than just exist. It had to compute. Researchers tested what those cardiac neurons actually listened to. They changed blood pressure, shifted blood chemistry, and altered how much the heart wall stretched with each filling. Each change triggered patterns of nerve activity inside the heart itself. Signals arrived, mixed, and produced a response. Pressure sensors reported how hard blood pushed against the system. Chemical sensors tracked oxygen, carbon dioxide, and acidity. Stretch sensors measured how full the chambers became, moment by moment. The key finding came when these inputs conflicted. The heart's neurons did not relay a single message upward and wait. They blended the information and reshaped their output, adjusting the timing of beats and the strength of contraction to fit the situation. Then came the harder test. What happened when the higher brain's influence weakened? In experiments where incoming commands from the brain were reduced or disrupted, the heart still did not fall silent or turn chaotic. Its intrinsic neurons kept monitoring pressure, chemistry, and stretch, and they corrected the heart's performance locally. The heart's basic rhythm continued, but now its fine-tuning looked less like obedience and more like on-site control. By the time modern systems biology took hold, the heart no longer looked like an isolated pump with a private wiring system. It looked like a partner in a larger network. Measurements showed a steady stream of messages traveling from heart to brain, not just the other way around. Some traveled fast through nerves, others moved more slowly through hormones in the blood. Together, they carried real-time updates about pressure, chemistry, and strain. As these signals reached the brain, patterns emerged. Changes in heart rhythm and the timing between beats lined up with changes in attention and reaction. Under stress, the heart's output shifted and the brain's stress circuits shifted with it. The feedback loop tightened. The body did not simply react to danger, it predicted, adjusted, and sometimes overcorrected. The heart helped set the gain on that entire response. Over time, researchers connected heart-to-brain input with emotional processing as well. When cardiac signals became erratic, people tended to show heightened vigilance, stronger startle, and harder recovery after stress. When signals became steadier, the brain tended to regulate more smoothly. The implication landed heavily. Regulation did not sit in one command center, it spread across organs. The heart acted as an active participant, shaping the brain's state. In present-day medicine, this knowledge stopped being just interesting and started becoming useful. When a heartbeat slipped into dangerous rhythms, clinicians no longer only blamed the brain or the muscle. They looked for misfiring circuits inside the heart itself. Electrical mapping traced where signals looped the wrong way. Then treatment targeted those exact paths, aiming to interrupt the problem without shutting down the whole system. That approach reshaped arrhythmia care. Catheter ablation used heat or cold to silence tiny regions that triggered chaos, often near nerve-rich areas where electrical and neural signals met. The goal stayed simple: remove the spark, restore order. At the same time, doctors started treating the heart's nerve inputs as adjustable controls. Vagal modulation attempted to shift the balance, slowing an overexcited rhythm or stabilizing a vulnerable one. Another tool quietly changed how risk got measured: heart rate variability. Instead of one heart rate number, clinicians watched the small beat-to-beat changes that reflected how the heart and its nerves adapted moment by moment. Low variability often matched illness, stress, or poor recovery. Higher variability suggested flexibility. Research used these patterns to track treatment effects, predict complications, and test therapies that supported the heart's own neural regulation. For thousands of years, the heart carried a reputation the brain never seemed to claim. People trusted it as a source of courage, of instinct, of truth that arrived before words. That belief survived because it matched experience. A fast heartbeat felt like fear. A steady one felt like calm. It sounded like knowing. But in today's reality, that old certainty ended up both wrong and strangely close. Modern medicine did not treat the heart as a second brain in the usual sense. It did not store memories. It did not form ideas. It did not think in language. Yet the evidence still pointed to something more than a pump. Inside the heart sat its own neural network, built from real neurons that sensed pressure and chemistry, compared signals, and triggered local decisions. That local decision-making carried a consequence that reached upward. The heart constantly sent messages back to the brain through nerves and hormones, and those messages changed the brain's state. They pushed the body toward alertness or recovery. They tilted attention, stress, and emotion before any conscious choice appeared. The heart did not replace the brain. It helped set the conditions under which the brain operated.